Picture London in winter, normally brisk, with its characteristic chill in the air. The city hums with a unique energy, a blend of history and modernity. But what if that familiar winter scene took a drastic turn? Imagine it's not just cold, but as cold as northern Canada, a region known for its harsh, unforgiving winters. Think of temperatures plummeting far below freezing, a bone-chilling cold that seeps into everything. The Thames, a river that has flowed through the heart of London for millennia, is frozen solid, its surface transformed into a sheet of ice. The iconic waterway, usually bustling with activity, becomes a silent, icy expanse. Snow piles high, blanketing the city in a thick white layer, and the city grinds to a halt. Transportation networks collapse, daily routines are disrupted, and the vibrant pulse of London slows to a crawl. The familiar sounds of the city are replaced by the crunch of snow underfoot and the whistling of the wind. This isn't science fiction, a far-fetched tale of a dystopian future. It's a scenario scientists fear, a plausible outcome if a crucial Atlantic current collapses. This isn't just about a colder winter. It's about a fundamental shift in the climate patterns that have shaped Europe for centuries. For centuries, this invisible river, known as the Atlantic Meridional Overturning Circulation, AMOC, has acted as a vital circulatory system for the Atlantic Ocean, keeping Europe mild. It's been acting as the continent's central heating, distributing warmth from the tropics towards the north, ensuring relatively temperate conditions for much of Europe. Without it, the continent would be a vastly different place. But as the planet warms at an alarming rate, melting Arctic ice is accelerating. This influx of fresh water is flooding the North Atlantic, diluting the salinity of the ocean and disrupting the delicate balance that drives the AMOC. This disruption threatens to weaken or even halt the ocean's delicate balance, with potentially catastrophic consequences. The risk? A dramatic shift in climate, a rapid and irreversible change that could reshape the world as we know it. This isn't a distant threat. It's a possibility that looms large, possibly within our lifetimes. The urgency of the situation demands immediate attention and action. The current in question has shaped European history, influencing everything from trade routes to settlement patterns. It's been instrumental in making agriculture and civilization possible in regions that would otherwise be uninhabitable. The warm waters carried by the AMOC have allowed for thriving communities and ecosystems in places that would otherwise be frigid, locked in ice and snow for much of the year. If it weakens or stops, we face one of the most dangerous tipping points, a point of no return that could trigger a cascade of irreversible changes. This is a critical juncture in our climate system, a moment that demands careful consideration and decisive action. The stakes are incredibly high. Scientists are now asking, if we broke the ocean's thermostat, pushing it to the brink of collapse, could we engineer a fix? Could we intervene in the natural processes of the ocean to restore balance and prevent disaster? This is the story of one bold, controversial plan to do just that. A plan that could either save Europe from a climate catastrophe or have unintended consequences that further destabilize our planet. At the heart of this unfolding climate crisis, a phenomenon lurks beneath the ocean's surface, largely unseen but profoundly impactful. It's a system so vast and intricate that its disruption could trigger a cascade of consequences across the globe. Is the Atlantic Meridional Overturning Circulation, or AMOC, a critical component of the Earth's climate system? Understanding the AMOC is paramount to grasping the severity of the challenges we face and the potential pathways to mitigating them. A massive, naturally occurring conveyor belt of water that spans the Atlantic Ocean. This isn't just a simple current, it's a complex, three-dimensional network of water movement that plays a vital role in regulating global temperatures and distributing nutrients. Warm, salty water from the tropics flows north, carried along the ocean's surface, acting as a natural heating system for the regions it passes. This warm water is a crucial source of heat for the higher latitudes, releasing heat that keeps Europe temperate, far milder than other regions at similar latitudes. Without this heat release, Europe's climate would be drastically different, potentially uninhabitable in some areas. As it cools and becomes saltier through evaporation, this water becomes denser and sinks near Greenland, a key location in the AMOC cycle. This sinking action is what drives the entire system, pulling more warm water north and driving the system, creating a continuous loop. This constant motion ensures the ongoing transport of heat and nutrients throughout the Atlantic. This process doesn't just warm Europe, its influence extends far beyond the continent's borders. It helps balance the planet's climate, acting as a major regulator of global temperatures and weather patterns. The AMEC redistributes heat around the globe, preventing extreme temperature imbalances, shapes weather patterns, influencing rainfall and storm systems, and supports marine life by distributing nutrients essential for the growth of phytoplankton, the base of the ocean's food web. But now, melting ice from Greenland and other Arctic regions is dumping vast quantities of fresh water into the North Atlantic, disrupting the delicate balance of salinity and density, making the surface less salty and less dense, hindering the sinking process that drives the AMOC. This influx of fresh water is essentially diluting the salty water, making it lighter and less likely to sink. This lid of fresh water sitting atop the denser, saltier water below could slow or even stop the sinking process, weakening the AMOC's circulation. The consequences of this slowdown could be catastrophic, threatening to shut down the AMOC, potentially leading to abrupt and irreversible climate shifts. The stability of this ocean current is far more precarious than previously imagined. If that happens, the conveyor belt stalls, disrupting the flow of heat and nutrients throughout the Atlantic and beyond. The implications of such a shutdown are far-reaching and potentially devastating. Europe chills, experiencing dramatic temperature drops, and global weather patterns are thrown into chaos, leading to more frequent and intense extreme weather events. The AMOC is a cornerstone of our climate. Its fate will shape the world's future, determining the stability of our ecosystems and the well-being of countless communities. The question, can we stop its collapse? Is there anything we can do to reverse this trend and restore the AMOC to its former strength? Some scientists think we might have to try, exploring innovative and potentially radical solutions to intervene in the ocean's processes. Enter the Underwater Parachute Plan, a bold and ambitious proposal to artificially enhance the sinking of water in the North Atlantic and bolster the AMOC. The proposal? Deploy hundreds of giant underwater parachutes in the North Atlantic to force surface water to sink, mimicking the AMOC's natural process. Each parachute, the size of a football field, would be towed by ships, dragging fresh water down into the depths. The goal: artificially restart the ocean's circulation, keeping Europe warm and the climate stable. It's geoengineering on a massive scale, an attempt to mechanically jumpstart the planet's circulatory system. The plan would require a fleet of specialized ships, operating non-stop in one of the harshest environments on Earth. It's a desperate measure for a desperate time. Here's how it would work. Ships tow 2 parachutes each, one open and one collapsed. The open parachute drags a column of surface water down as the ship moves, mixing the ocean layers. At the end of the route, the parachute collapses, the other opens, and the ship turns back, creating a continuous cycle. Multiply this by hundreds of ships, 24/7, and you get a massive artificial downwelling. The aim: move enough water to keep the AMOC alive. It's a logistical and engineering challenge on a scale never attempted. The hope is that this brute force approach could buy us time. But can we really nudge a current this powerful? Supporters say the parachute plan is a last resort emergency brake. The physics is simple. Push enough water down, and you pull more in from the south, just like unclogging a slow drain. Unlike other geoengineering ideas, this one is adjustable. Ramp it up or down as needed, and test it on a small scale first. Proponents argue that since human activity caused the problem, we have a responsibility to try to fix it. They see this as a bold use of human ingenuity to avert disaster. But even they admit it's not a perfect fix, just a possible lifeline. The real question is whether it's even feasible. And that's where the critics come in. Critics argue the Atlantic is simply too vast for parachutes to make a difference. The energy needed to move that much water is staggering, far beyond what a fleet of ships could provide. There's also the risk of unintended consequences, disrupting deep-sea ecosystems, harming marine life, or triggering new problems we can't predict. The project's carbon footprint could be huge, burning fuel to fight a problem caused by burning fuel. And the cost? Astronomical. Money that could go to cutting emissions or renewable energy. Many warn that techno-fixes distract from the real solution, stopping greenhouse gas emissions at the source. Prevention, not risky intervention, should be our focus. If the AMOC collapses, Europe could see winters as harsh as Siberia's, with agriculture devastated and economies upended. The effects would ripple worldwide, shifting rainfall, droughts in Africa and South America, floods elsewhere, and chaos in global weather patterns. The oceans would suffer too. Less oxygen in the deep sea, collapsing fisheries, and stressed marine life everywhere. Social and economic fallout would be massive food shortages, mass migrations, and political instability. Ports could freeze, trade could halt, and millions could be forced to move. This isn't just a cold snap. It's a global humanitarian crisis. The stakes are enormous, and the clock is ticking. That's why some scientists are willing to consider radical solutions. Hollywood's The Day After Tomorrow made the idea of a Gulf Stream shutdown famous, but the real changes would unfold over decades, not days. The film's core message, that disrupting a key climate system can have catastrophic consequences, is grounded in real science. The movie helps people grasp the stakes, but risks making the threat seem like fiction. In reality, the disaster would be slower, harsher winters, crop failures, and relentless economic disruption. The parachute plan is an attempt to write a different ending, one where we intervene before it's too late. It's not a Hollywood fix, but a real-world gamble. The question is, should we take it? The parachute plan, while seemingly radical, highlights a fundamental debate at the heart of climate action. It forces us to consider the different paths we can take to address this global challenge. Should we engineer our way out of climate trouble, relying on technological innovation and large-scale interventions to counteract the effects of greenhouse gas emissions? This approach emphasizes human ingenuity and our capacity to solve complex problems through scientific advancements. Or should we instead focus on restoring the planet's natural balance, prioritizing conservation, emission reduction, and sustainable practices that allow ecosystems to recover and thrive? This path emphasizes a more holistic and preventative approach, working in harmony with nature rather than against it. One path bets on technology and human ingenuity, believing that we can develop the tools and techniques necessary to mitigate the worst impacts of climate change. It's a proactive stance, confident in our ability to control and manipulate the environment. The other urges humility and prevention, recognizing the limitations of our knowledge and the potential for unintended consequences. It advocates for a more cautious and sustainable approach, minimizing our footprint and allowing natural processes to heal the planet. Critics warn that meddling with complex systems could backfire, leading to unforeseen and potentially catastrophic consequences. They argue that we don't fully understand the intricate web of interactions within the Earth's climate system, and that interventions could disrupt delicate balances. While supporters argue we may have no choice if the crisis deepens, suggesting that geoengineering might be necessary as a last resort to prevent irreversible damage. They believe that the risks of inaction outweigh the potential risks of intervention. The truth may lie in doing both, a balanced approach that combines technological innovation with ecological restoration, cutting emissions drastically and transitioning to clean energy sources, while simultaneously researching emergency interventions, exploring potential solutions for the most dire scenarios. The parachute plan isn't a perfect solution, and it comes with its own set of challenges and uncertainties. But it forces us to confront the scale of the problem and the risks we're willing to take in the face of a changing climate. It highlights the urgency of the situation and the need for bold action. Our choices now will shape the climate for generations to come, determining the kind of world we leave behind for our children and grandchildren. Will we gamble on engineering, hoping that technology can save us from the worst consequences of climate change? Or double down on prevention, investing in sustainable practices, and reducing our impact on the planet? The future of Europe and the world may depend on the answer as we navigate the complex challenges of climate change and strive